Well, hello, folks. Welcome to the lecture on Chapter 11, Multiple Comparisons and Analysis of Variance. So let's get going. So, a couple of important learning objectives for this chapter. One is understand the problem of multiple comparisons in the overall significance level, right? And this deals with what happens when you start getting to a situation where you're making multiple comparisons between different groups, right? And you'll see why that's relevant here in a minute. Know how to apply the Bonferroni correction to multiple hypothesis tests and confidence intervals. Now, I will say this, that even though this is covered in your chapter, in no place will you actually have to pay much attention to this either in your homework or going forward. So, in some ways, if you don't get this whole Bonferroni, sounds like a dance, doesn't it? But if you don't get this whole Bonferroni thing, don't worry about it. I'm not even going to really talk about it in this lecture, okay? Um, Understand how the F statistic allows us to compare means of multiple groups by comparing the variance within a group to the variance between the groups. So this point here is really the essential point of what I'm going to be talking about. And really what this chapter is about. So frankly, much of this early stuff on Bonferroni is really just a proof. I mean, in reality, it's really nothing that most people really pay more attention to. I'm kind of shocked that the textbook gave as much space to that topic. It shows you how to do something that it then ultimately concludes that you should not do. Okay, so if you follow that train of thought in the book, okay. And then be able to perform and interpret an ANOVA procedure to analyze potential associations between a categorical predictor variable and a numerical response variable. Okay, so really what this chapter is really about is in fact these last two bullet points. Okay, the first two bullet points are really just to make a case for why you need to run an ANOVA anytime you actually have more than two groups. If you recall, Chapter 9 focused on what to do when you're comparing two groups. Okay, and so we learned how to apply the t-test, particularly the two-sample t-test when you're comparing two groups, right? Everything that's really in the first part of this book is basically about why you can't do that when you have, say, three or more groups, right? It's not just a matter of running, say, a t-test between the three groups. And that's really all that stuff is about, okay? So if you just automatically buy into the idea that an ANOVA is what you need to do when you have three or more groups, right, then we basically begin with where these latter two bullet points are, okay? All right, so let's talk about this idea of multiple comparisons. Right, what happens when you're trying to compare multiple means? Okay, and once again, this is kind of what's the point that's made at the beginning of the book, so I'll kind of cover it quickly here. But let's suppose that we wanted to compare the mean prices at four supermarkets, say on a particular it could be overall prices or say on a particular product, doesn't matter, of course. And you learned in chapter 8 that when we are computing statistical tests, right, we have this thing called the alpha, which has to do with the amount of risk associated with making a type 1 error. Right, recall type 1 error is basically the error that we make when we say, hey, I found something, right? And you didn't really find anything, okay? We try to minimize that, right? So we don't engage in false advertising, okay? So the problem is, right, if we use the logic that we use, say, in chapter 8 and chapter 9, we would end up with 6 different hypotheses that we'd have to test, right? If you recall, this idea of mu is just a way of saying mean. So the first hypothesis, remember there's always two hypotheses. There's the null hypothesis, which suggests that there's no difference between the groups. Okay, that's what the equal sign would imply, right? If you say that something's equal to something else, you're saying that there's no difference. Whereas the alternative hypothesis, which is generally the hypothesis that we're making, has the not equal sign, right? So we're saying that alternatively, we're arguing that the mean of A, right, this would be a supermarket, is not equal to the mean of B. Okay, so that's basically our hypothesis. That's our null, that's our alternative, right? And so think about it for a minute. Not only would you have this mean of A compared to mean of B, but then you would also have to compare supermarket A with C. okay? And then A with D, okay? See how this is going? And then B with C, and then B with D, and then lastly C with D. So we end up with 6 different hypotheses. The problem with that is that this alpha actually gets multiplied in that sense. So we end up with a large chance, right? Basically, if we did the math, about 26% rather than 5%, right, that at least one of the tests will result in a type 1 error. Okay, so that's just too much risk, right, when we're trying to keep it at 0.05. So this is really kind of all of what the first part of this chapter is saying to you. Okay, so for that reason, we have to do ANOVA, okay, which stands for the analysis of variance. Okay, so on ANOVA, so let's suppose, right, that we have some survey data, okay, and on one of those variables is categorical. And by the way, this is just another way of saying that we are dealing with groups. Remember, we are talking about how to compare groups. Groups represent a categorical variable, like something like, a college rank, right, or marital status, or occupation, right? All of these are groups, which means that it's a categorical variable. But we're comparing them on some quantitative or numerical variable, right? So, something like test score or anxiety or anything that can be quantified, right? And so these are really the situations. So, for example, you would not use ANOVA when you have 2 categorical variables, right? So if we were, say, comparing marital status on something like sex or race, okay, that would not be a case for ANOVA, right? Because both of those are categorical. Nor would we if we had 2 numerical variables. Okay, if you recall, that's the condition for, say, doing a correlation or doing a regression. Okay, so one of your variables has to be categorical. Normally it's the independent variable, and then the other variable has to be numerical or quantitative. That would be the dependent variable. Okay, and so what does the ANOVA do? Well, it tests to see if the means from the different categories are not all the same. Now notice how strange that is to say that. Okay, we could have just said we're going to test to see if the means from different categories are different. Okay, but remember that the way statistical analyses work is we test this idea of the null, right? And remember, the null says that they're all the same, and so ultimately what we're trying to do is see if we can reject the null. So that's why it's sort of stated in this awkward way, are not all the same. Okay, it's just a backward way sometimes in which science seems to work. Okay, so this would be our new null, okay? And that is we're basically looking to see if it's true that the mean for group 1 is equal to the mean for group 2, and on and on and on, okay? And so in that case, rather than having 1 versus 2, 1 versus 3, 2 versus 3, right, we can state it this way because we're going to test all of these all at the same time. And of course, the alternative hypothesis is that at least 2 of the means differ from each other, right? In other words, the only thing that we need to make this not true is that any one of these, right? If we had 10 of them, as long as 2 of them are significantly different, it would in fact lead to a rejection of the null hypothesis, okay? And so this minimizes, right, the kind of test that we're doing, right? At the end of the day, we're just going to test and see if there are some differences. Now, this is going to be important because you're also introduced to the concept of a post hoc analysis, okay? And I'll talk about that later, but, it factors into what we're doing here. So I'll prime you a little bit. Okay, so how does this thing work, right? And this is kind of the logic of it. And let me say this, that, one of the interesting things about statistical tests, and that is that, even if you don't get this logic that I'm about to give you, if you at least pay attention to the steps that I'm going to follow up with next, you can still work your way through this, right? So I'm just going to kind of explain what it's actually doing when it does the statistical tests. But then, once again, at the end of this, it's really a matter of you just kind of following the steps and making the right decisions, okay? So remember, this thing's something called the analysis of variance. Okay, analysis means to dissect something. So what we're doing with this statistical test is we're ultimately going to dissect the amount of variance that is within groups and compare that to the amount of variance that exists between the groups. Okay, so what does that look like? So let's take an example, right? We had our 4 grocery stores, and let's suppose that this is kind of what it looked like, right? So for each group, this is just basically all the prices, right? If we did that, we have the word responses here, but these could stand for anything. So let's just say they're prices, okay, on some metric. And where you see the red dot is, right, this would be the means, okay, for the groups. Now, I want you to notice, right, that there's a lot of variance within each of these groups, right? All the blue dots would reflect every price or product, if you will, that is within a given group, right? And notice that there's a lot of variation within the groups. Notice there's very little variation between the groups, right? So all the red dots are kind of pretty much in the same place, okay? So that's small variation between the groups. But like I said, there's a lot of variation within these groups. Okay, see that? And all of them, the variation is kind of about the same. A little bit more variation on D here, but pretty much the same. Okay, so this is a situation where we have little variation between the groups because the means are pretty much all in the same spot, but we have a lot of variation within these groups. Okay, now compare it with this one, right? Where in this case, right, we have a situation where there's small variation within the groups, right? All the dots are pretty clustered close together, okay? But there is tremendous variation between the groups, right? These means are differing quite a bit. Okay? And so these sort of reflect, 2 potential situations that you could have. You could have a situation in which when you look at the variation in means, you have a situation like this. There's very little variation between groups, but there's a lot of variation within the groups. Or you can have a situation like this, where there is very small variation within the group for each of these, but yet the variations between groups are considerably different, okay? Especially between, say, group A and group C. So, an ANOVA results in an F statistic. You might recall me saying that every statistic gives you some kind of letter, right? We were introduced to the X bar with the mean, the S with the standard deviation, the R with the correlation coefficient, the B with the regression, and then the T with the t-test. Well, the ANOVA gives you an F statistic. Oftentimes we call it the F ratio. And that F ratio is basically defined by the variation between the groups, right? So if you think back to the picture we just saw, right, divided by the variation within the group. So you see it's a ratio. Sometimes we call it the ratio of between groups by within groups, okay? So if we were to think back at our notions here, right, now notice there's very little variation between the groups, right? So this number would be small, and yet a tremendous amount of variation within the groups, right? That would basically suggest that this would result in a small F statistic, okay? But if you think about our other scenario, right, where we have very little variation within the groups, right, so this number would be small, but yet tremendous variation between the groups, that number would be big, that would actually result in a fairly large F statistic, okay? So the larger the F statistic, basically it's going to suggest that you're getting more of an effect, right? That there's more likely going to be a situation where the difference between groups is going to be statistically significant, okay? So one of the things that's also different about the ANOVA, other than the fact that it's an F, and that is that this time, rather than getting a single piece of information, say the F, you actually get something called an ANOVA table, okay? And so that'll be different. So let's sort of use an example here. Let's suppose that we wanted to compare the mean of ounces of foods for various breeds of cat, okay? In my past life, I've actually done this kind of research for a local company that you might know, okay? So let's suppose that what we have, so if we ran an ANOVA, right, we would get something that looks like this. Virtually all statistical packages, especially